Hi, everyone. Welcome to Vector Space Talks. My name is Neil Canungo. I'm your host today. I'm joined today by developer advocate at Qdrant, Terry Damiba, and founder of Superlinked, Daniel Svanava. Terry, you want to say hi? Daniel, you want to say hi?
How's everyone doing out there? Thanks for joining us this morning or evening, depending on where you are in the world.
Hey, happy to be here. I think maybe it's one of the first ones you guys are doing. I love the graphic. Yeah, let's get this on the road.
Yeah, definitely. Glad you all are joining. Great to see you all joining our live stream. We are getting our live streams going more regularly on a more predictable cadence. We're aiming to do these on the second Wednesday of every month. So you can expect to see these coming more often on your LinkedIn Live. We're also streaming on YouTube and on Twitter or X, however you want to call it. So you can find us on any of the three platforms. We're going to talk today about metadata awareness with embeddings. But before we get into that, and Daniel from Superlinked is going to be presenting that core topic. But before we get into that, I'm going to present a little bit on what's been going on with Qdrant, just a few minutes while people trickle in. I have I have 4 or 5 slides just to show everyone what's going on, the latest in the community with Qdrant. And so let's get started. So first thing I wanted to let everyone know about is in just a couple weeks, on September 26th, we have our first ever community conference / meetup that is our large scale in-person get together in Berlin. We're expecting over 300 people. It's September 26th. We have tons of partners that will be there. AWS, Microsoft, Vultr, Base 10, Gina, Llama Index, N8N, 12 Labs. You can see them all on this slide right here. So if you want to sign up for that, go ahead and put I love Qdrant in the DMs, and I'm going to send the links out for this and other things, or put I love Qdrant in the chat, and I'll DM you the link for here, as well as a discount code for you to sign up for our Vector Space Day, conference. Next, I wanted to also mention that leading up into this conference, we have our Think Outside the Bot hackathon. So this hackathon is a non-chatbot hackathon using Qdrant. You can also use Superlinked and one of the various partners that you see on the screen here for bonus prizes. There's over $10,000 in prizes and bonus prizes for several $1,000s in credits and cash that you can get for using bonus technology. It's online, virtual. Anyone in the world can participate. You still have another week to submit. We have had a lot of people sign up, but we've only had a handful of submissions. So that's still, really good odds of winning. If you want to, get your submission in, really encourage that. We're starting to see the submissions trickle in now, but you got time for this. And again, put I love Qdrant in the chat, and we will DM you the link for this after the session. Next thing I wanted to talk about is Qdrant stars, in case you didn't know about this. So I've had a lot of people send me blogs or try to ask how they can get involved with Qdrant, contributing in Qdrant. And I wanted to mention the Qdrant stars. It's our community advocacy program. We give out over $1,000 a month with Qdrant stars for people that are contributing blogs and content and doing meetups that are related to Qdrant. It's a great way to help you get involved with the community and help Qdrant grow, and Qdrant to help you grow. So this is a program for you. If you want to join Qdrant stars, we have an application form that I'll send out as well. Highly encourage it. We do monthly rewards, and we do travel budgets. We do swag. We do all kinds of cool things for Qdrant stars. So recommend checking that out. And while I'm on the topic of our community, please join our Discord. We have over 8,000 members in our Discord. We have tons of experts in there. We have our CTO, Andre, in there. We have Terry, myself. We have Jenny. We have the whole DevRel team, all in Discord, answering questions, helping the community, posting their latest blogs. Community is posting our blogs, helping each other. It's a great way to get going in Qdrant and get help on anything you need, as well as network with other Qdrant users. And a great way to get involved is also in our office hours, which will be next Thursday on September 18th at 11 a.m. Eastern. That's going to be hosted on the Discord platform. So you'll see a link for that when you join Discord. And then lastly, I just want to talk about some recent feature enhancements for Qdrant. So in Qdrant 1.14 and 1.15, we've had enhancements with quantization, new 1.5 bit or 1.5 bit and 2-bit quantization, as well as asymmetric modes, help cut memory use while keeping accuracy. So these are ways to really, compress your data and improve your performance of your retrieval. So you can check that out. MMR re-ranking. Terry just did a meetup on this in San Francisco on Monday. Super cool way to diversify your search results so that you're not getting duplicate search results just based on similarity. You're also getting diversity. So this is a really cool feature I'd recommend looking into. HNSW healing allows you to rebuild your index kind of like on the fly. And score boosting allows you to implement business logic. And we've introduced decay functions as well for ways that you might want to implement rules to boost the relevance of certain results, boost the relevance of certain results based off of business logic or different criteria. And this is all really relevant in today's session when we're going to talk about metadata awareness and powering up your embeddings with Daniel. And Daniel's got an enhanced approach, another approach to improving your embeddings and getting those results. We talked about re-ranking, we talk about score boosting, we talk about these different methods, but Superlinked has an interesting approach here, and Daniel's going to talk a lot about that. So let me get this banner off Daniel's face there so you can see him. There you go. So without further ado, I'm going to hand it over to Daniel. And also, just to let everyone know, you can go ahead, before I hand over, there's 2 minor notes. You can put your questions in the chat, and we will answer your questions live. You also can check out this recording on YouTube after the session. So this will all be recorded. So without further ado, Daniel, handing over to you.
All right. Thanks a lot again for having me. As Neil was saying, feel free to ask questions, during the presentation. I would love to make this interactive. I think we have a way to pull those questions up on the screen as well. Let's just dive right in there. So basically, this will be a conversation, and I'll be using a very specific set of examples that hopefully help you understand what we mean by adding metadata into the embeddings themselves. But it really applies to pretty much any retrieval problem where you are really trying to search amongst objects that are composed out of all kinds of different properties, and you are sort of trying to navigate a set of trade-offs between using those different properties to find the right answers. The example I'll be using is the joint project that we have been working on with Qdrant. We have this basically running in production in a real-world deployment, but we have also covered, and explained these techniques in joint content, and the content is out there. I'm sure we'll be able to kind of link it. And then, also, if these topics are interesting, then feel free to connect with me afterwards and ask questions, and I'm always happy to explain and help. So we'll be using the problem of searching for hotels as a example and motivating example for this technique. And what better way to imagine what's going on than by looking at a query. So let's say you have a query that says, popular family-friendly hotels with good Wi-Fi near Manhattan Midtown under 400. And again, this could be, you are looking for Jira issues that have a certain combination of factors going on with them, pieces of knowledge base. But in this case, we take the example of hotels. This kind of query really tests all your kind of retrieval skills. You have to bring a bunch of tools from your tool belt to handle something like this. And the reason is that, things like the word popular will have no semantic representation in, let's say, the description of the hotel, or worse yet, maybe every hotel will claim that it is popular. And so it's rather, a reference to some other property of the hotel, maybe a popularity counter, maybe a popularity counter in a given location or with a given type of users. And then, family friendly could be that you have some taxonomy of categories for your hotels, and you want to find something at the intersection of certain categories like that. In e-commerce we have catalog kind of hierarchy of categories that's very similar. And then good Wi-Fi is something that we might be observing in reviews of these hotels, but it's kind of textual semantic kind of element of the query. Maybe we have to figure out how to aggregate all these thousands of reviews to kind of bring out the right semantic kind of attributes of these objects we are searching through. And then near Manhattan Midtown will be a location bias, and under 400 is some kind of filter intent, right? So you can think about the under 400 as a filter, right? That should just be translated into a filter. But everything else is kind of a bias. And I don't mean the bias word in like a negative sense. It's basically you want to lean towards certain aspects of your data, right? You want to lean towards the popular hotels, towards the family-friendly hotels, towards the near Manhattan Midtown kind of hotels. And you want to combine all of these objectives together, right? And that's what we mean by metadata, right? Like where the hotel is and how popular it is. Typically, that's some kind of property that's outside of what you think about, okay, I'm going to put that into the embedding itself, right? You might be today taking an embedding of the hotel description or maybe the reviews, but basically with Superlinked, our goal is to make all of these representable by the underlying vectors. And basically, I'll describe why that is useful. Now, in reality, this problem also keeps getting more complicated, right? Because it really matters who is doing the searching. So this is a user that might be in certain location already. And the user might have some history of purchases or interactions with the website. You might have some statistics of what gets booked this time of day or season, and then what similar kinds of users actually want, right? Am I making sense so far, Thierry, Neil?
Yeah, definitely.
Yeah.
I think what you're saying is that just the semantics alone are difficult to rely on. So there's a lot of, sorry, my phone's going off. There's a lot of, numerical and categorical location biases that are in there that you can start to quantify differently.
That you want to sort of drive towards, and at the end of the day, somehow find the compromise of all of these things that then is the hotel that the person actually wants, right?
Especially with numbers, we know that, for example, LLM might think 40 and 400 is closer than 400 and 399. So you need to do some special stuff in there to make sure that you're actually capturing the difference between the numbers.
That's right. So if you're trying to, let's say, have this as a JSON object, and you want to run the whole object that represents all these properties through a text embedding model, that text embedding model will kind of latch on the nouns in there, and the numbers will be kind of butchered, right? So they'll be tokenized, like strings are tokenized, and things like call currents on the internet will drive the distance that the embedding model kind of encodes between numbers or even locations. There is just a very vague idea of the map encoded in these models, and so there will be a lot of noise if you do that. Okay, so how does this? This is like, I'm not the one who invented that people want to do this kind of querying in all kinds of different contexts. So typically, the tools that we bring to bear on these sort of problems involve, on the left side, we'll have some inputs, right? There will be the conversational query, there will be some context of the user, there will be some context of the overall situation, which page I'm searching from, what's going on. And then I'm trying to convert this to a set of operation that the underlying index offers for me, right? So the operations are some kind of pre-filtering, boosting on different properties, the vector, the kind of more traditional textual semantic search with embeddings. There are re-ranking capabilities and maybe post-filtering once I see some distributions of these results. And this is kind of, then, you have to do the translation from the left to the right, and it's probably some kind of LLM that helps us generate that query object that then gets executed by the underlying database and combines all of those things on the right. Of course, the question there is the kind of latency of that translation, right? We all heard, especially pre-LLM, people were quite obsessed about latency. This kind of went away with AI search a little bit, but it's, I think, still relevant. And then the reliability, if we are generating very complicated queries, how likely are we going to get those queries correct? And, that's where evals help and all of that. So that's kind of the first problem. How do we go from left to the query on the right so that the underlying database knows what to execute? And then there are some elements of how efficient that execution will be, right? How efficient can the index boost on metadata properties while traversing the underlying, HNSW nearest neighbor graph, right? And we can get into that nuance later on as well. But those are kind of the two elements of this conversation. How efficiently and reliably are we translating the query and the context to the actual query that the system can execute? And then how efficient is the system executing that query? And are there some trade-offs there? Make sense as a kind of two orientation points?
Yeah.
Okay. And, typically, this is something that everybody should figure out for themselves. It's hard to find a solution that can do the metadata boosting while traversing the approximate nearest neighbor graph. And so then it's typically some kind of sequence. So you do the semantic search and then you re-rank on the metadata boosting, for example. Or you pre-filter and then you traverse the graph and then you re-rank. So typically this is not done in the same traversal. That's the kind of second bucket of concerns in terms of recall and latency. Okay. So just to kind of talk about a little bit, and maybe here I'm taking kind of a more extreme position, but just for the purpose of getting people to think about this stuff, right? Again, people should run evals and load tests and so on their own data. It's always kind of comes out different than what you expect, and you shouldn't take any of this stuff as sort of gospel. But I sort of usually urge people, when I had that example of near Manhattan Midtown, for example, right? You could think about, okay, well, we can create some kind of bounding box on the map and use that as a filter, and that's going to take care of that. The problem with this is that, in fact, the user's preference is not a binary function of like everything beyond this line I don't care about at all, and then everything within that geometry, amazing, right? It's some kind of smooth function, right? So if it's 1 meter beyond the boundary of what normally I would consider Manhattan Midtown, but it's otherwise an amazing hotel, I probably still want to see it, right? Same with popularity, you might be thresholding on popularity. Everything above 4 stars is popular, great. So I'm converting the popular part of the query into like a threshold filter. But in fact, if something is 3.9 and otherwise amazing, amazingly fitting all the other properties, again, I want to see it, right? So just kind of urge people to think about, hey, which of these should really be filters versus I want to make some kind of boosting. And I think people kind of under boost, so they don't use this as much as they could. So that's kind of first observation. The second one is the reliance on re-ranking. It's just so easy to put the re-ranker on top of your system and improve the metrics in very real way, right? So it's a great place to start. But then you can't pull half of your database out and re-rank it for every query. It just doesn't work, right? So if I have a database where I have t-shirts and pants, 50-50 split, and I want popular pants, I can't pull all the pants out of the database and reorder them by popularity. This is not going to work, right? This is too much data moving around, too much compute spent reshuffling this. So re-ranking is not the end all be all. So people should just consider the trade-offs again. And then the last one we already mentioned, right? If you have some kind of data object and you want to take advantage of the vectors themselves to find the right objects, if you start by just taking the object and using a text encoder and making a vector out of it that way, that vector will not encode all the different properties of the object because it will treat it like string and it will, have those issues that we already mentioned. So these are kind of three areas that I think are worth looking into once you have built your first version of the system and you are looking to optimize something. Any questions from the audience? Don't be shy. Maybe people have some experience with this from their own projects and they want to share something.
Well, I think it's definitely a bolder statement, right? To say, some of these approaches will make your search sad. So like Hakan said, metadata is sad, and I'm not sure if, he was just kind of kidding around there. But yeah, I think that, there's like these different approaches. And like you said, like doing your own evals is really important. But this is these are some interesting points on like how you improve that accuracy or those results in your retrieval.
Mm-hmm. Okay. So, in the absence of these three things, what can we do better? And our answer to that, and in fact, the answer of like if somebody builds a two-tower recommender, a two-tower network-based recommender system, the way that system is trying to handle this problem is that it's trying to encode as much of the signal as possible into the underlying embedding, right? So that when you do the vector search, all the right stuff comes out. And the input to that is the user object and the item, for example. Analogously, if you train your own encoder for natural language search in a kind of big tech setting where you'll be training that encoder from scratch, you are trying to use as many of these signals that are available in that encoder so that the candidate generation before the re-ranking has the best possible recall, and you don't have to retrieve thousands and thousands of candidates. So basically, the more you can do with putting information into the embedding itself, carries those benefits. And then you shouldn't try to, of course, filter with dense representations. That doesn't really make sense. And so there, the filter functionality of the of Qdrant, of course, is very useful, right? So in principle, you should be able to do everything with filtering and the right kind of embeddings, and maybe combination of dense and sparse embeddings if you, for example, care about keywords. So we'll be sort of focusing on those. And that brings us to this kind of mindset that everything is a vector. And I think, that's where we probably find some common ground. We think about, something like a user in your product. You should have an embedding of that user that encodes everything you know about the user, right? You should, be able to create embedding of query that, again, covers all these different biases that the query is asking for. And then it's very easy to, for example, personalize the results by, pulling the query vector towards the user vector, or evaluating which of the results is more relevant or less relevant. So once you get away from this kind of very complicated boosting and kind of re-ranking structures back to just everything is a vector and we look at the distances between these things, it kind of simplifies the mental model a little bit. And then basically, what we do is, and what you then need at the end of the day are these orange boxes. Is basically the boxes that help you convert the context we had on the left side, the natural language query and the context and so on, into the filter, predicate, and the embedding. And then do the same thing for the data that you are indexing with your database. So in e-commerce, in the hotel search example, it would be product catalog and some user metadata, and of course, behavioral events. In, let's say, enterprise search, it would be, of course, lots of JSON objects and PDFs and so on. So, that's where those models factor in, because you want to be doing the symmetric thing of like encoding a query to the same space as you encode the data you are indexing. This should be quite straightforward. Okay, and there are, of course, many approaches. The best approach is to train a custom encoder, right? So you just train a model on the queries that you are getting, on the data objects that you have available. You have some source of signal, like are people clicking these things or not? And you train an encoder that just takes everything, feature engineer these entities, you make an encoder. So like a two-tower network, or basically single encoder. This is what you would do when building, let's say, a media platform in big tech. That's kind of my background. I was at YouTube for 6 years, but it's data intensive, and it takes time, and it takes patience. And so in the absence of that, our approach to this problem is to basically have Lego blocks for embedding models. And out of these Lego blocks that understand different aspects of the data, like the numbers and categorical properties, and of course the text and images, but also things like relational data, relationships through graph embeddings, and we have our own location encoder and so on. By stitching these encoders together into basically a model, you are able to eat something like a hotel object and make a vector that encodes everything you know about that hotel. And the same way then about the queries on the other side, so that the underlying database can then match between the two, right? And we can handle the queries that we have seen at the start. And this is from the article that we wrote together, where it highlights how the underlying way we actually do it is super simple. It's no sort of rocket science. And also the framework that does it is free and Apache 2.0, and anybody can go and use it. So we don't gatekeep this information. And it's actually quite simple, and you can kind of just do it at home. And this is a simple example of that. Just imagine that I have a query that says very popular pants, and I have products where I have description and popularity properties, right? One is string and one is a number. And I want to create embeddings that help me match something like a query that says popular pants to these kinds of products, right? So normally you would try to generate from the populars, let's say, some kind of filter or a boost. Here we just make an embedding that encodes, hey, I want bias towards popular things, and I want bias towards pants within one embedding. And the way you do it is through basically concatenation. And this is the simplest way to aggregate these embeddings. There are more sophisticated ways, but you can start by concatenation. So let's say you have two encoders, one that eats numbers and one that eats strings. They both produce embeddings that are at most one long, so unit normalized. So I get from, I put the number into the green box and the description into the orange box, get two vectors out that are at most one long, and I dimension-wise concatenate them and put it into the database. So far, so good? Simple?
Yep.
Okay, so I put this into the database, and it's kind of each of those components contributes equally to the magnitude of the resulting vector. So it's kind of de-biased, right? We care equally about the description and the popularity rating in terms of the indexed data. And then on the other side, when I get a query that says, let's say, very popular pants, I need some sort of LLM over here that says to the green box, hey, create me a bias towards positive numbers, and hey, create me a bias towards pants. Again, these two things produce embeddings. But here we can, for example, multiply those with a scalar, right? So now, because I said very popular, this thing can decide, okay, I want the positive bias, but I want it 5 times bigger than the default because it's very popular. And then I want my encoding of pence over here. And again, I can dimension-wise concatenate this stuff. And then, the underlying database only produces a dot product sort of distance, right? So it finds me all the data vectors that maximize this sum, right? And because of how dot product works, which is like the first dimension is multiplied with first, and then we add to it the multiplication of the second dimension with the second dimension, I can multiply and scale these components on the query side and experiment, and basically that's the boosting, right? But the underlying query will just traverse that super efficient nearest neighbor index of yours, right? It doesn't have to figure out, okay, how am I boosting and traversing the vector search index? It doesn't have to do that because we are doing all of it within the embedding itself, right? So the query can be super efficient. It will only traverse like a very small part of the data, but we will be using it to combine both the kind of popularity and semantic match with the description type objective into a joint objective. So then, the 10 things that come out of the database will be both pens, or very likely pens, if you have them in there, and they will be popular at the same time, right? So you don't have to rewrite, you don't have to do anything. Okay. So I mean, if there aren't questions here, then we don't have anybody actually watching. So.
Oh, we have quite a few people watching. So
okay. So am I making any sense?
Intently listening, and I actually do have some questions, but I'm going to hold them a little bit till the end. So.
Okay. I can then kind of go back to the different slides, but this is the core idea of the approach. And the cool thing is that these boxes can be anything, right? They can be graph embeddings, they can be time series embeddings, they can be, of course, text and images, locations, right? So the problem then only turns into, hey, can we come up with all these Lego blocks that we are combining? And then, can we have some framework that helps us stitch these things together? And then, there's some stuff that I'm not going to go into, like aggregations of these vectors. Let's say making a user vector by averaging a couple of these kind of composite vectors of the products the user interacted with. You can do all kinds of, math on top of this, but this is kind of the core underlying idea of the Superlinked framework, to kind of give you both the ingestion side of this and the query handling side of this.
So one question did come in just now from the audience. So LinkedIn user asked how to define and control the vector sizes of all-in-one encoded query from one side and documents to be retrieved on the other side to make this work.
Yeah, I mean, you want the same system to do both. So, in Superlinked, you kind of define the...
I hear you right now. I don't know if you want to unmute.
Sorry?
Can you hear me? Maybe it's just me.
I can hear both of you.
I can hear both of you also. Okay, we good?
Oh, I think it's just my audio, sorry.
Yeah, can you maybe bring the question back up? But basically the question is, okay, well, if I'm doing this kind of magic over here when I'm processing the data, and I'm doing this kind of magic over here to process the queries, how do I make sure that these things are aligned, right? Like these different dimensions kind of mean different things. And yeah, like it helps to have a framework that keeps track of this, keeps track of where each of these numbers came from, so it can align the vectors between the, it can align the query vector to the data vector. It can make sure that it's going to be the same dimensionality, and the sub segments will mean the same things. And it all starts with basically kind of defining this data model, like my products, my users, my events, the relationships. And then you define index, like here is my index that combines all of this and puts it into Qdrant. This is all Python code in which you kind of declare these things. And then you run Qdrant and Superlinked on top, and the system is kind of taking care of the alignment of those embeddings.
And we have one more question from O. Is this recommended for big data?
Right. So And big data means different things for different folks. Certainly, adding more dimensions to your vectors increases the amount of consumption of the database. And the same kind of dimensionality reduction techniques apply, and so on. The biggest indices that we have running in production with customers, let's say, are up to 2 terabytes. So, you can have a 2 terabyte worth of index. You can put a couple thousand dimensional vectors in there, and because you have loaded everything into those embeddings, you can have a bunch of different use cases then running on top of that index, right? So it's not just, hey, let's do search, but we can do recommendations, we can do user lookalikes, because we don't have just products, but also users in the index, and that's good for marketing, for analytics. So once you have everything in there, it's then easier to deploy a bunch of use cases within your team, your organization.
Awesome.
And then Qdrant just talked about quantization. Obviously, that's compatible with this and very much helps.
I had a question about multimodal embeddings, and sorry, I guess I messed up my audio earlier, but I'm back now. So how do you, is this mostly for plain text embeddings, or can this be used with multimodal embeddings as well?
Right. So, I mean, these encoders, I would say I'm trying to find the right words to describe it, because, when people hear multimodal, they think text, image, video, audio, right? Let's say that's where it sort of ends. And you can certainly have encoders for those data types. Let's say you have a support case and you have like a voice memo from the person coming in. You have like, some transcript of that, maybe conversation with the support assistant. But then you also have a timestamp of when it came in and some kind of categorization of which bucket it landed in, and maybe a couple other properties. And so for us, you should make an embedding out of all of that, not just the voice and the text, and you can certainly do that here, but also when the ticket actually came in. So you kind of lean and prioritize perhaps tickets that are in a state that really needs help, or they have been sitting there for a little bit too long, right? So I don't know, maybe we can take a poll of like what is beyond multimodal, but most people don't think about, okay, numbers in the embedding alongside of all those other modalities. Those numbers are important, like I don't know how we kind of got so comfortable not putting them into the vector in the first place.
What about like high cardinality values like IDs or SKUs or something that have lots of numbers? Does this like explode the dimensionality of your vector embedding?
Yeah, I mean, certainly if you have a categorical, let's call it categorical property like IDs with millions of potential values, there isn't really a benefit of, there is no semantics behind that ID, right? So it's not actually useful as a part of the embedding. It's basically a random number. And so if you want to, let's say, do a filter on ID, right? Hey, give me object with this ID. You should use the filter that the database provides totally, right? Now, if you have semantic IDs, there has been this idea circulating, right? If you have some way to assign IDs that make similar items or similarly purchased items or similarly kind of, Jira ticket with similar root causes, if you can make an ID out of that, then basically you have built the embedding model and it can be one of the encoders. And then by definition, that encoder will be denser and it will put similar things in similar places in the embedding space. But then why not complement it with a number encoder that injects kind of the severity of the issue and potentially other properties like that. So yeah, like don't make vectors with 50,000 dimensions. And that's where we also kind of can touch on the sparse. In our kind of basic approach, all of these encoders produce dense encoding, more or less dense, right? But of course, things like keyword search, where you want exact match on specific keywords, or BM25, they benefit from sparse encoders. And so you can think about it maybe as two stacks, like you have a stack of dense encoders and then separately underneath, you can have a stack of sparse encoders, and then you have to figure out if your database supports traversal through those two indices at the same time and can score between, or you will do rank fusion, you will do a sparse, retrieval, and dense, and then merge the results. Of course, if you can do both at the same time and score across, it's better for recall.
Have you, maybe this is a silly question, but have you tried this with like multi-vector support with Qdrant and having both dense and these kind of packed embeddings, like having them both in your collection?
Mm-hmm. So when you say multi-vector, we mean stuff like the late interaction, Colbert, Copali, that sort of thing. Mm-hmm. Yeah. So there is a way to extend this framework to those concepts. You can think about you can in some ways think about multi-vector representations as a way to re-rank results. So basically, okay, so maybe just for the benefit of the audience, when we think about multi-vector, basically we describe a situation where, let's say this individual text encoder doesn't produce one vector to encode, let's say, description of a hotel, but multiple vectors. And then, equivalently on the query side, we don't have one query vector, but for each token of the query, we have a vector. And then the way this is used is you basically, for each query token, you do a separate query into the data, and then you do union, and then you re-rank that on the distance of those sets of vectors, right? So that's like multi-vector quick explanation. This is helpful if you have long text, right? And so far in our applications, we got away with sufficiently big single vector models, and we benefit more from combining them with the metadata encoding and kind of add those dimensions. But yeah, this is something that we very actively are working on. How do we extend that and add the capability to do multi-vector stuff? And that's where we'll also lean on our database partners, right? Because for that, the re-ranking step is needed, and it's useful, and it should happen in the database.
Okay. We have quite a few questions coming in on the chat, actually. So
maybe like I'll just kind of take a checkpoint for the folks who are sort of we're going for 43 minutes. Basically, if any of what I have described so far makes any kind of sense to you, or you have more questions, this is a link to our GitHub. You'll find the Qdrant connector in there, and you will find the rest of the framework. And again, I'm on LinkedIn posting about this stuff all the time. So I'm super happy to take more questions now, but basically that's kind of my call to action for today, is that people should check out the repo and kind of give us feedback there and try it out. And we have this deployed in production in a bunch of places. We had some people winning hackathons with the framework because it's still quite, I would say, niche or is not super well known. So it can give you an edge in a hackathon. And in fact, as Neil said, we sponsor also the Qdrant hackathon. So do check it out and give us feedback if you have this situation where it's not just the text and image that matters for you, but you have metadata or semi-structured data, and you want to treat it as nicely as your text and images and as smartly. Okay, cool. Let's do next question.
Okay, yeah, we'll try to get a couple more questions and then we'll wrap up. So Sudhanshu was asking, do you have any benchmarks available? So as you were actually talking about kind of some of the multi-vector and some of the tests you were doing, I was wondering the same thing. Do you have any benchmarks or evals that you've done comparing things like hybrid search to the metadata-aware approach?
We have benchmarks coming out. So our current website and sort of most of our communication has been frozen in time. Interesting thing about benchmarks is that the MTEB table and all the commonly used data sets for information retrieval benchmarking are text query and text payload, right? That's why also Sudhanshu is asking about, hey, can we compare to BM25 plus dense representation of the text, right? The problem with this is that in reality, you have all those other properties attached to your data, and those those properties are important for the query to find what it needs. And so we couldn't just use those benchmarks. We had to make our own benchmarks, and this is super tricky. But we are basically there. We compare with, let's say, a dense encoder and splayed, which that should cover kind of the sparse and dense combo, also asked here. So basically, stay tuned is the we compare both to kind of full stack AI search solutions and some of these kind of build it yourself setups as well. Okay. I want to, however, make it a little bit clear that we are not saying that, hey, somehow this way you can do text search better, right? The text search is only as good as the text encoders you'll be using as a part of your encoder stack, right? So we can just demonstrate that, okay, maybe you split the text into some parts and you encode them separately, and then the query understanding piece splits it intelligently between those, and you can get pretty decent results. But that's sort of not the point. The point is that we have sort of, as a community, I think, underinvested in looking at the outside of the text part of the data, and we want to just catch up on that front with what we can do for text, all these wonderful things, and then combine that together and then advance on these fronts kind of in parallel. So that's the way to think about it.
Okay. And then I think we have time for like one more question. And this is, I think, relating to when we were talking earlier with multi-vectors. So it's more of a general question. Mu was asking, again, rewinding it back when we were talking about multi-vectors, can these two vectors increase storage and query time? How can dimensionality be reduced without losing accuracy? And I know you had mentioned quantization, and I don't know if you have some other advice for Mu here.
Yeah. So surprisingly, I mean, storage, yes, right? So you have to store bigger vectors. The vectors are a fraction of your total database consumption, right? So if you increase the vector size, you don't get the same kind of multiple increase on the overall database consumption because you also have fields for filtering in there and so on, right? So we find that if you, let's say, double your vectors and the vectors are 30% of your overall data in the database, is not, very big effect on the overall price. In terms of the query time, because you are using the index to do the searching, you are only traversing some neighborhoods in this graph. If you have twice bigger vector, this doesn't mean it's going to be twice slower, the actual query, or not necessarily or not quite. So quantization still applies. Dimensionality reduction, making these boxes output fewer dimensions, and then having an eval for how many dimensions and what quantization is enough. All of that still applies. And here we are just saying, hey, add more of this information in there, and we help you encode it efficiently, and you get all these benefits that now all of it matters for your dot product or cosine similarity.
All right, cool. Well, thanks, Daniel. I think we're kind of running up on time. I just wanted to tell everyone just our little plug here. Just if you guys want to get started with Qdrant, we have the open source Qdrant. We also have Qdrant free tier available on Qdrant Cloud. That's free forever, 1 gigabyte of memory. So go ahead and sign up for that. And also wanted to mention that we have recently introduced cloud inference on Qdrant Cloud. So you can, actually create your embeddings, since we're talking about embeddings today, create those embeddings directly in Qdrant Cloud. And that's a great new feature. So check it out today. And just wanted to thank you all for joining, and thank you, Daniel, for joining us as a guest today. And we appreciate
Thank you for hosting.
Yeah.
Thanks for coming out, Daniel. Appreciate it. Superlinked is working on some cool stuff.
Yeah, see you in Berlin. I think we'll be hitting the circuit, hopefully getting some good beer. I moved to US and good beer is in a shortage over there, so I'm looking forward.
Yes, sir.
And for anyone watching, just again, put I love Qdrant in the chat and we'll DM you the links. So thank you again. And yeah, I'm looking forward to that beer in Berlin as well. See you there, Daniel.
All right. Have a good one, everybody.
Thank you.
Thank
Bye.
you. Bye.
Cheers.